Hello students, welcome to the lecture on set, and after the lecture we will be able to learn the following objectives. Understand the concept of set theory, explain the operations on sets, discuss the partition of sets, explain the Cartesian product of sets, understand Venn diagrams. Let's start with a brief introduction to set. The concept of set is fundamental to mathematics and computer science. Everything mathematical starts with sets. Relationships between two objects are represented as a set of ordered pairs of objects. The concept of ordered pair is defined using sets. Natural numbers, which are the basis of other numbers, are also defined using sets. The concept of function, being a special type of relation, is based on sets, and graphs and diagrams consisting of lines and points are described as an ordered pair of sets. Though the concept of set is fundamental to mathematics, it is not defined rigorously here. Instead, we rely on everyone's notion of set as a collection of objects or a container of objects. Let's now learn about the concept of set theory. The word set in mathematics was first of all used by George Cantor. According to him, a set is any collection into a whole of definite and distinct objects of our intuition or thought. Cantor's definition faced controversies due to the forms like definite and collection into a whole. Later on, a single word distinguishable used to make the definition acceptable. A set is represented by using all its elements between braces and by separating those from each other by commas if there is more than one element. Two forms of representation of a set: set builder form representation of set and the tabular form or roster form representation of set.
The simplest way to describe a set would be a container. And as a container, a set contains objects. In discrete math, these objects are usually referred to as elements. An example of a set can be just about anything, such as a box of crayons. In this case, each crayon is an element of the set box of crayons. Another example would be a football team. In that case, football team is a set and each player is an element. Now, since this is supposed to be math, let's try a set that contains numbers. For example, let's make a set called S and let it contain some numbers. The notation that we use for a set is the name of the set followed by an equal sign, and then the actual elements of the set within a pair of braces. Now let's look at the elements. In this case, we can see that 3 is an element of the set, but 6 is not an element of the set, and we notate this by adding a little slash through the element symbol. So what if we want this set to go on past 5? What if the set goes on to infinity? Obviously, writing out each element would be impossible, so we use an ellipse to symbolize the fact that this pattern continues indefinitely. So here we can say that the set S contains all positive integers, starting with the number 1 and going on forever. Notice that we can go in the other direction too. In this case, we have the set of negative integers. So what if I wanted to define a set as all of the integers that are between 2 and 7? Now I could simply do it like this. But what if the set is bigger? What if the set is, say, all of the integers between 2 and 100? Now there's different ways to do this, but one way is to use a variable, like x or y, as a placeholder, and then define the scope of x. So this is basically the same as the first one, but we've defined x using greater than and less than operators. Now the line in between the x's is usually translated as such that. So if I'm reading from left to right, I would say s equals x such that x is greater than 2 and x is less than 7. The advantage of this kind of notation is that we scale very easily. So I can quickly replace the 7 with 100 or whatever I need, and I have a much different set. So this was just a very basic introduction to set theory. In the next video, we'll look at some more things that you can do with set builder notation.
The types of set. Singleton set. A set having single element is called a singleton set. Pair set. A set having two elements is called a pair set. Finite set is a set having a finite number of elements, that is a set where counting of elements is possible, is called a finite set.
Saw how to define sets and their members through the use of set builder notation. In this lecture, we will learn about several types of relations between sets. One such relation is equality. If two sets contain exactly the same elements, they are said to be equal. For example, set A, which consists of the elements 1, 2, and 3, and set B, consisting of the elements 2, 3, and 1, are equal, since they both contain the same elements. Notice that it doesn't matter that their elements are listed in different orders. This is because the order in which the elements of a set are listed is irrelevant. The set consisting of 1, 2, and 3 is exactly the same as the set consisting of 2, 3, and 1. The list does not imply that there is any particular order to the elements. It only says that every element listed is a member of the set. So if sets A and B contain the same elements, then they are equal. Another important relation between sets is the relation of subset. If all the elements of set A are also contained in set B, then we say that set A is a subset of set B. This relation is denoted using the subset symbol. If two sets, A and B, are equal, then they are subsets of each other. This is because all the elements of A are members of B, and all the elements of B are also members of A. So any two sets that are equal are subsets of each other. And since every set is equal to itself, every set is also a subset of itself. So the subset symbol can be used whenever all the elements of A are also members of B, whether A has the same number of elements as B or has fewer elements. But when A has fewer elements, we can be more specific and call A a proper subset of B. We denote this using the proper subset symbol, which is the subset symbol without the line underneath. In addition to the relation of subset, a set can also be a superset. In any case where set A is a subset of set B, we can also say that set B is a superset of set A. This relation is denoted using the superset symbol, which is the subset symbol reversed. Likewise, if A is a proper subset of B, then B is a proper superset of A. But what about the empty set? The set containing no elements. The empty set is considered to be a subset of every other set, including itself. In fact, the empty set is the only set which is a subset of every set. So far, we have represented sets by listing their members.
Given the set A, the power set of A is the set of all subsets of the set A. The power set of A is denoted by P, open parentheses A, close parentheses. Example 1. Let A be a finite set with cardinality n. What is the size of the power set P, open parentheses A, close parentheses? Our options are n, 2 to the n, or n squared. The answer would be 2 to the n. And why is this? Because for every element within the set A, it can either be in the set, in the power set, or out of the power set. Therefore, you have 2 times 2 raised to the power of however many elements are within A, which gives you 2 to the n. So the size of any power set is 2 to the n, where n is the cardinality of the set.
where I'm talking about the vowels in the English language, the letters A, E, I, O, and U. And all I'm going to be talking about is those vowels, nothing else. I can say that's the universe that I'm going to be talking about, and I'll call those letters my universal set. I'll designate the universal set usually with a capital U, and then I'm going to say that U equals the set containing A, E, I, O, and U. Now let's say I want a subset of this. Let's say I want a subset A, and subset A is going to consist only of the letters A and E. From this subset, I can create another subset, which I'm going to call the complement of A. The complement of A, which is going to be written as a capital A with a line over it, is going to be all of the letters in the universal set that are not in A. So the complement of A is going to be the letters I, O, and U. The complement of A is also a subset of A, a subset of U. And if I combined A and the complement of A, I would have all of the letters that are in the universal set.
Closed set, there are several equivalent definitions of a closed set. Let S be a subset of a metric space. A set S is closed if the complement of S is an open set. S is its own set closure. Sequences, nets, filters in S that converge do so within S. Every point outside S has a neighborhood disjoint from S.
Okay, this video we're going to be talking about closed sets. We've already discussed quite a lot about open sets, but we haven't really touched on the idea of a closed set. You know about closed intervals if you've done real analysis, so let's go ahead and define this. If we have a topological space, say x tau, then we say that C, a set C, which is a subset of X, so some subset of XC is closed if its complement in the space is open. So as a diagram, let's say U is an open set. So let's say U is in tau, and let's draw U. Let's say U is an open kidney again in this space. So that's an open set. Then we say that the complement, so X, the space without this set U, is a closed set. So this is including all these points which aren't included in our open set. So it's basically everything outside here. So all of this, including the boundary, is a closed set, because all of this inside here, not including the boundary, is an open set. So if a set is open, then its complement in the space is closed.
Let's learn about operations on sets. Unions. A union is essentially the act of adding multiple sets together to combine the elements into a single set. Intersections. An intersection makes a new set from the common elements of the sets involved. Complements. There are two complements, the relative complement and the absolute complement. Describing a set. Roster method. The roster method simply lists all the elements in the set. Set builder notation. The second method of describing a set is set builder notation, where a set is described using the following format: A equals to mode of x, where x is an even integer which is greater than 0. We will now discuss about partition of sets. A set partition S of a set is a partition of set into subsets called parts and represented as a set of sets. By extension, a set partition of a non-negative integer n is a set partition of the integers from 1 to n. The number of set partitions of n is called the nth Bell number. There is a classical lattice associated with all set partitions of n. The infimum of two set partitions is a set partition obtained by intersecting all the parts of both set partitions.
Right, S, which is a subset of the power set of A, which just means that the S is going to be a collection of some subsets of A. Right, and this guy is called the partition of A if it satisfies these following three conditions. Right, first condition is if you look at each element of this partition. So for all element x in this partition S, each element has to be a non-empty set. So make sure that there is no empty set. Right? Second condition, if you pick any elements, say x and y, from this partition, from this set S, right, they are either identical sets, so x equals y, right? If they are not identical, they must be disjoint. So if you look at the intersection of two sets, it must be in an empty set. Right? And last condition, if you put together all the elements in S, so each element is a set, so we take the union of all the sets in this partition, and they basically add up to the entire set A. All right, a partition is actually a very simple concept, but these three characteristics will make it a partition. So here's what we're doing. So let's say this is set A, which has 1, 2, 3, 4, 5, 6. All right, partition is simply doing this. All right, we're going to make a subgroup. All right, so maybe I'm including 1, 4, 5 and to make up a subgroup. Maybe second subgroup might be just 2 by itself. And then third subgroup would have 3 and 6 in it. So, which is actually listed here. Right, S1, right, first subgroup would have 1, 4, and 5. And a second subgroup has 2. And third subgroup would have 3 and 6. All right, so let's make sure that this satisfies the condition. So let's list so condition number 1 and the condition number 2 and the condition number 3. All right, let's check the first one. All right, so every single subgroup has to be non-empty. So you can see that this is not empty, this is not empty, this is not empty. So it satisfies condition number 1. All right, number 2. Right, so it has to be pairwise disjoint. So if you pick any subgroup, they cannot share any element. You can see that. Oh, actually, here you can see that 1, 4, 5, 2, and 3, 6. None of them share anything. So you can see that it's satisfied here. And third condition, it has to cover the entire set A. So you have to have 1, 2, 3, 4, 5, 6. You can see that 1, 2, 3, 4, 5, 6. Everyone's covered. So it is covered, satisfied. So therefore, S1 is a partition. Right? Let's check the second one. Right off the bat, that we notice a problem. So here we see an empty set here. So condition number 1 is actually violated already, right? For the fun of it, let's look at the other two. You look at any two subgroup, and they are pairwise disjoint. So number 2 is okay. And number 3, does it cover the entire set A? 1, 2, 3, 4, 5, 6. So everyone's covered, but the condition 1 is violated. So S2 is not a partition. Right? How about number S3? Right? You can see that here there is no empty set, so you can see that condition number 1 is satisfied. But second one, pairwise disjoint. But you look at the first subgroup and the second subgroup, there is a common element 4. So therefore, it is not pairwise disjoint. So condition 2 is violated. Right? Let's look at 3. Does it cover everything? 1, 2, 3, 4, 5, 6. So number 3, condition number 3 is satisfied. Right? therefore S3, because condition 2, number 2 is violated, it's not a partition. All right, the last one, all right, there's no empty sets, so condition number 1 is satisfied. Right, they pairwise disjoint. You can see that the 1, 2, 4, 5, 6, there's no common element, so condition number 2 is satisfied. But the last one, you can see that you have 1, 2, and misses 3, 4, 5, 6. So 3 is missing, so condition number 3 is violated, right? Which means that S4 is not a partition.
Let's now understand Cartesian product. Ordered pair. A pair is a set which have only two elements, like A and B. A pair can never have more than two or less than two elements. It always has exactly two elements. Denotation of Cartesian product. The Cartesian product of two sets A and B is the set of all ordered pairs AB, where the first element of ordered pairs A belongs to the first set A and the second element of ordered pairs B belongs to the second set B. Let's study Venn diagrams. A Venn diagram is a visual representation of any given set. In Venn diagram, the rectangle box indicates universal set U, and we can show other sets by making small circles in that rectangle box. Intersection, union, complement, symmetric difference, relative complement.
Actually, they're kind of my favorite. So first of all, when we talk about set A, that's actually all the stuff in the circle for A. That's set A. When we talk about set B, now that's everything in the circle for B. So all of that and all of that. And you'll notice that some of A and some of B intersect. And finally, you'll notice this big U. That actually means the universe. And that means everything in A and B, and even outside A of B, everything in that box. So let's look at a couple examples. Let's look at our first here. Well, this guy, that means union. That means all of it together. United. So if I'm going to take everything in A, my set A, my circle A, and unite it with everything in B, well, let's see what that's going to look like. Everything in A and everything in B. So this would be my answer if I'm shading for A union B. Let's look at the second one. This upside down U actually means intersect. And what intersect means is where A and B collide, or where they're the same. Think of an intersection where two roads come together. Well, where would that be? Well, where A and B are the same is right in here. So that would be your answer if you're shading the Venn diagram for A intersect B. Now we're going to use these two in the next ones. Now this time we have an A with a little slash. That means A prime or A complement. They mean the same thing. And actually, they mean everything outside of A. So let me shade everything outside of A. This is outside of A, and this is outside of A. So if I was going to shade just A complement, that's all the green stuff. But when I look here, it's A complement union B. So that means we're going to include everything in B. So this is also in B. So if I was going to shade this Venn diagram for the answer A complement union B, this is what I would have. So let's look at the second one. This time I have A intersect B prime. Wow, well that means where A and B prime are the same. This one I'm actually going to shade B prime first, everything outside of B. Now I need to look, well where is my A at? So I'm just going to draw little lines for my A. So everything in this circle for A is A. But remember, this means intersect. That means where are they the same? And they're the same everywhere that I have my pink lines and my orange shading. So let's fix this one. So this would be my answer. Notice the shaded part is outside of B. So that's my B prime, anything outside of B. But it also includes A. So everything that was shaded in B prime and A. So this would be my answer for this one. Now when we look at this Venn diagram, we actually have three sets, A, B, and C. So that's why we have three circles. But remember, our rules apply for this one too. So I want to find A, union B, union C. Well, remember, union means putting it all together. So if I want to do A union B, well, remember, that's just putting everything in A with everything in B. Okay, great. But I also have this union C, which means I need to put all of it together. So let me shade C. So this would be the picture, the shaded picture of A union B union C. Now let's look at the intersect. So this time I'm talking about intersect. Remember, that's this symbol. Now that means where A intersects B intersects C. Remember, that means where they're all the same, where they all touch each other. Okay? So this one gets a little tricky. I want them to all touch each other. If I'm standing here, am I also touching C at the same time? Nope. So I know that one doesn't work. If I'm standing here, am I touching A at the same time? Nope. So I know this part isn't part of my answer. And the same goes for here. I'm not touching B at the same time either, am I? So I know this isn't going to be part of my shaded region or my answer. I'm sure by now you've probably figured out that the answer is right here. Because when I'm standing there, I'm standing in A, B, and C all at the same time. And that's kind of what intersect means. It means all at the same time.
Now in the end, let us summarize what we have learned in this lecture. A set is any collection into a whole of definite and distinct objects of our intuition or thought. A set is represented by using all its elements between braces and by separating those from each other by commas. A set partition of a non-negative integer n is a set partition of the integers from 1 to n. Cartesian product of set A and B is not equal to Cartesian product of set B and A. A set having infinite number of elements, that is a set where counting of element is impossible, is called as infinite set. A Venn diagram is a visual representation of any given set. In Venn diagram, the rectangle box indicates universal set U, and we can show other sets by making small circles in that rectangle box.